In this module, we're going to look at the Atlantis deeps on the floor of the Red Sea, where we have significant accumulations of laminites with high levels of copper and zinc in those laminites. And these Atlantis II deeps are often considered a contemporary zinc-copper ore deposit. They're sometimes grouped with SedEx, lead-zinc deposits, and at other times people have argued because of the elevated copper levels they're relevant to sedimentary copper as well. And so the question I want to ask in this presentation is it a classic stratiform or strata-bound sedimentary copper deposit, or is it a SedEx deposit? Or is it a halokinetically brine-focused metalliferous accumulation with aspects of both deposit types? The Red Sea, in terms of its regional tectonics, is a relatively young, active rift system which is salt-floored in that it contains Badenian Middle Miocene salt. And we see a range of north-south transitions from more continental influences in the north of the Red Sea into more open oceanic rift associations in the southern Red Sea. It's one of the youngest marine zones on Earth, and it's propelled by what is an area of relatively slow seafloor spreading, about 1.6 centimetres per year. The block itself, the Arabian Plate, which is driving that extension, is rotating in an anti-clockwise direction. And so at the southern end of the Zagros fault belt, we have subduction rates of the order of 22 millimetres or 2.2 centimetres per year, while at the northern end of the plate, we have rates of 16 millimetres or 1.6 centimetres per year. And that rotation of the Arabian Plate into the Eurasian Plate is causing the eastward movement of the Eurasian Plate and the expulsion in a pincer movement of the Anatolian Plate moving to the west. Strike slip related to that rotation is taken up along the Gulf of Aquifer Dead Sea Transform Fault, which is the western boundary of the Arabian Plate, which has a rotational movement in a predominantly northeasterly direction. But for our purposes, what's most important about this Red Sea axis is that there are significant accumulations of salt within the Red Sea depression. This was known as early as the 1960s, when DSDP wells 225 and 227 penetrated into what was the top of a thick halokinetic Miocene salt deposit. And the top of that salt is mapped by the S horizon, and it's defined as the first top salt marker in the basin succession, and clearly shown in both the bulk density values and in the porosity values as we penetrate the top of that salt in DSDP wells 225 and 227. So this was a Middle Miocene rift-to-drift megahalite deposit, which is now undergoing halokinesis. And here we can see those intersections in the top of that salt in 225, 227 and 228. 225 and 227 actually recovered halite. 228 just recovered the anhydrite edge rock at the top of that succession. So the Red Sea evolved from continental crust some 30 million years ago into an incipient rift, so that by 10 million years we had sufficient drawdown and hydrographic isolation to allow a very extensive megahalite to accumulate in the Badenian in the Red Sea Rift. It was then flooded, and certainly by 5 million years ago it was flooded by normal marine waters, and since then we've had the lateral migration of the evaporite unit, shown in purple, migrating in over the newly formed oceanic basaltic ridge. Today we have a series of sediment loading and gravity slides creating active salt allochthon tongues, as seen in the image on the right, adjacent to what are the various brine deeps. And seismically we can see the S horizon, the top of the salt, and we can see the subsequent Pliocene fill atop that S horizon marking the top of the salt. And we can also see that this halokinetic salt does in places retain some growth stratigraphy in the evaporites. That salt is extremely important for two reasons. We're seeing collapse at the crest, in this case of a salt anticline, and you can see the evaporite anticline there with a crestal collapse on it. That's telling us that that salt is dissolving. Throughout this extent, the edge of this halite unit is dissolving and creating sodium chloride-rich brines seeping through the overlying and adjacent sediments Also, although we haven't imaged it, it must also be occurring on the underside, forming a lateral underbelly dissolution residue with brine seeping down into the underlying volcanics and volcaniclastics. Throughout the axis of the Red Sea, beneath waters which are more than a kilometre deep, we see there's something like 26 brine pools where these dissolution brines coming off that halokinetic salt are accumulating. And some of these brines, indicated here by the black circles, are accumulating metalliferous sediments. And we're going to focus in on that region of the Atlantis II Deep, the Valdivia, the Wandoo and the Discovery chains in that succession, where the Atlantis II Deep is highly metalliferous. It is the most metal-rich brine pool in the Red Sea. Throughout the Red Sea sump, these brine deeps are located in the axial trough and they're separated by intertrough zones. Quite often these are lateral faults and they are floored by younger basaltic crust. And throughout the sump we don't see magnetic anomalies in the basement older than 1.7 million years. Toward the northern end we see much smaller deeps and only isolated deeps within the axial depression, and some of them are still accompanied in that northern part by active volcanic activity. In the southern area we see a more mature terrain with namakhirs or salt allochthons creating brine pools in the closed deeper parts of the axial troughs. So here's an example of a spillover pond. This is in shallower water on the edge of a deep in the Gulf of Aqaba, the Neom Pond. But the same process is happening throughout, where we see these brines with microbial mat fringes on them forming these hypersaline pools in the lowermost parts of the deeps. If we look at the brine chemistry broadly, just looking at sodium versus chlorine, we can see that the Atlantis II southwest and northern troughs, which I'll explain shortly, have some of the highest salinities in the brine pools in the succession. And we can actually plot up the brine pool chemistry and we see that near linear progression indicative of brines derived by halite dissolution throughout the various salinity profiles of the brines in the various brine pools in the Dead Sea Deep. So there's a mixing line with Red Sea deep seawater at the lower left and the Atlantis deeps at the upper right, showing us a dissolved halite source for those various deeps, with the most saline being the metalliferous Atlantis II deeps. If we look at surface topography on that set of salt sheets, we can quite clearly see that throughout Red Sea deeps, this is done in the vicinity of the Atlantis II Deep, there are tongues of allochthonous salt migrating out over the basalt. These are namakhirs. We can see the deepest positions indicated by stars in amongst these flowing salt sheets, with the direction of the salt flow indicated by the white arrows. So don't think of the Atlantis II brines as non-evaporitic. They are surrounded by tongues of flowing and dissolving allochthonous salt. And here's a transverse view of the same thing, and we can see how these various brine-filled sumps on the seafloor are fed by brines coming in from the dissolving edges of these halokinetic Miocene salt masses. It's also a region very likely where rift volcanism is supplying both the heat for fluid convection in the subsalt positions, and it's also allowing us to have a copper source in those subsalt brine focusing positions that then accumulate those metalliferous brines, those hydrothermal waters, in those bottom brine ponds. These subsalt brine interfaces are focusing the hydrothermal escape pathways and focusing the lateral flow of those brines into hot, density stabilized brine sumps on the Red Sea deep sea floor. So we can see that here. We can see the S marker in the left-hand image, the top salt. We can see it in the Bouger gravity anomaly and in the combined image on the right. And the stars are indicating the positions of the various deeps. And we're focusing in on the position of the Atlantis II Discovery deeps in the central part of that image. They're metalliferous, and we can see that quite clearly here when we look at the levels of copper, here measured in percent for the Atlantis deeps, and also zinc, also measured in percent. Remember the positions here. This is the Atlantis II Deep we're talking about, and adjacent to that is the Wandoo Basin, the Valdivia Basin, which are somewhat metalliferous, and the Discovery Chain basins, which are somewhat metalliferous, but much less so where we're looking at values for Wandoo, Discovery and Valdivia in both copper and zinc measured in ppm, not in percent. Notice also that there are elevated levels of cobalt in the Atlantis II Deeps, and we'll come back to cobalt when we get back into our main discussion in later modules of the various redbed sedimentary strata-bound copper deposits around the world. But for now, let's just note that these deeps in the Atlantis II brines are relatively enriched compared to the other deeps across the region. So let's compare the general chemistry of those fluids, and we can see that the Atlantis II Deeps are elevated in terms of temperature. They are amongst the hottest of the various deeps. They are the most acidic amongst the various deeps that have been sampled. They are the most saline in terms of their chlorine content. They also have elevated calcium relative to magnesium ratios. We can see that they have high levels of dissolved silica, high levels of potassium, high levels of lithium, and high levels of manganese compared to the other deeps. And likewise, if we continue this discussion of the brine deeps, we can see that the iron levels in the Atlantis deeps are extremely high, as are the zinc levels, whereas the sulphate levels are quite low. And in terms of the dissolved inorganic content, we see less depleted carbon-13 values in the brines of the Atlantis II Deeps. So if we summarise, the metalliferous Atlantis II bottom brines are somewhat hotter, more acidic, they're highly saline, they're enriched in calcium over magnesium, they're silica enriched, they're relatively sulphate depleted, and they're enriched in potassium, lithium, iron, zinc, copper, manganese, and their dissolved inorganic carbon show somewhat enriched carbon-13 values, more positive carbon-13 values. Now, all of these brines in these deeps are convective bottom sump mixtures that contain combinations in various proportions of salt dissolution chloride-rich brines and the subsalt hot magmatically heated hydrothermal waters that have mixed and combined with and flush metals from the volcanics and the volcaniclastics, and then they sit in these hot brine pools and cool. So let's now focus in on the Atlantis II Deep, where we can see that there are 4 deeps within that Atlantis II Deep. There's a northern zone, an eastern zone, a southwestern zone, and a western zone. Core 684 sampled the western basin, Core 683 sampled the southwestern basin. When we look three-dimensionally at the Atlantis II Deep, we can see that it's surrounded by halokinetic salt, and then within the sump, the brine lake or the dal itself, in that deep seafloor sump, we have density stratified brines. The lower brine is at around 61 degrees centigrade, and the upper brine is around 50 degrees centigrade before transitioning up into normal marine Red Sea deep seawater. So the Atlantis II Deep is host to one of the largest known modern hydrothermal ore deposits on the modern seafloor. It's our only modern analogue for what are halokinetic brine pool type base metal accumulations, and we'll come back to this notion of why this is such an interesting area in terms of both copper models and lead zinc models throughout this course dealing with sedimentary copper, and also the next course looking at lead zinc base metal deposits. So focusing in on the brine layers, we can see that the brine layer is not made up of one, but a number of brines. And that can be seen in the thermistor, the in situ temperature measurements in the brine column, and also in the salinity profiles in the brine column. So that once we exceed depths of a little less than 2,000 metres, the bottom temperature starts to rise, and at around 2,000 metres it jumps from values of the order of low to mid-20s up into values in excess of 50 degrees centigrade, with the lowermost brine column having temperatures as high as 67.5 degrees. That thermal stratification is also reflected in the same levels in terms of the salinity profile. Now, the temperatures are relatively stable, but they do alternate, they do rise and they fall according to how much hydrothermal input we have coming into that lower brine pool. So the temperature of that lower brine mass has been steadily rising since the 1960s. And so by 2008, the bottom temperature had risen from around 61 degrees to 67 degrees. Likewise, the structure of the transition zone between about 1990 and the dense bottom brines at around 2,000 metres below sea level has changed and increased slightly since the 1960s. By the mid-1990s, when more detailed thermistor profiles were available, it was shown to contain not one but two main convective layers with nearly constant internal temperatures of 61 and 55 degrees respectively. That is, layers 2 and 1. This is a long-term, thermally stratified, salinity stratified brine pond system sitting in the Dow, that is the Atlantis II Deep. If we look at the bottom sediments, we can see that lithologically there are four main units in core 464 and two main units in core 683. And those units are defined as the amorphous silicate layer and also the upper sulphide layer, constituting Unit 4 in the Western Basin. And that's underlain by the central oxide, the metalliferous pore layer, shown in orange, with Units 3A through F in the Core 684 subdivisions. Then there's a lower sulphide SU1 in Unit 2, and then the lowermost unit, Unit 1, which defines the onset of metalliferous accumulation, which is a detrital oxide pyrite layer. In the Southwest Basin in Core 683, we only have the equivalence of what is considered to be Units 3 and 4 present in the system. But there is a much greater thickness of metalliferous sulphide-rich mineral, SU2, in that upper unit in Core 683 in the Southwest Basin. There are varying proportions of sulphides indicated in red, iron hydroxides indicated in orange, manganese oxides and hydroxides in yellow, and hydrothermal anhydrite indicated in grey, with backgrounds of carbonates, detrital silicates, and quite significant proportions of clays, and in the lower section some magnesian phyllosilicate clays in the lower section of the Southwest Basin core. What's also interesting here is that where we have lesser amounts of anhydrite, we have more sulphides. And that's reflective of the fact, as we'll discuss shortly, that anhydrite is a retrograde salt. It becomes less soluble as the temperature increases, which is the opposite of most of the other phases we're considering. So if we look at it in terms of the density stratification in the brine column, there's 1990 as our onset transition coming out of the normal Red Sea deep waters at about 24 degrees. We have the manganese oxide facies. Then as we go into the upper convective layer, it's equivalent to the conditions that favour the precipitation of iron oxides. And then in the lower convective layer, where we get the silicates and the sulphides accumulating, we have our hottest brine temperatures and also our hottest salinities, as we can see in the chlorinity profiles, and also our most acidic conditions in terms of pH, going from a pH of 8.4 in the deep normal bottom waters of the Red Sea through to a pH of 5.2 in that lower convective sulphide-rich layer. That zonation of the various orthogenic bottom sediments is a reflection of the thermal and density layering in this hydrothermal Dow brine column. In these pools, the prime driver is cooling of the brine. We can see that for all of the sulphide phases, as we cool the brine, going from temperatures of say 200 degrees down to 75 degrees centigrade, we can see there is a decrease in the solubility of those different sulphide components and also of the iron carbonate components. Contrast with that is the calcium sulfate, the anhydrite curve. The calcium sulfate becomes more soluble at lower temperatures. It's a retrograde salt. And that's the reason for that inverse relationship between the presence of anhydrite, which indicates probably warmer temperatures, and cooling when the anhydrite goes into solution and the sulphides accumulate. So this is the cooling effect driving the precipitation of sulphides in these hydrothermal bottom brines. This is not the redox interface effects we've been emphasizing as forming most of the world's red bed sedimentary copper. This is a different animal. The deep sediments consist mostly of a combination of chemical and clastic sediments, clays and various chemical and biochemical precipitates, with varying inputs from basin-scale hydrothermal and detrital sources. Now, a characteristic feature across most of the metalliferous sediments is this millimetre-scale layering of the sediments, and it gives them a superficial appearance to banded iron formations in the Precambrian. This laminated succession is obviously indicating quiet, quiescent bottom conditions without a lot of bottom reworking of sediments when those brines are cooling and the sulphides are accumulating. Likewise, we see the iron oxyhydroxides, the hydrothermal carbonates, and the sulphides in the orthogenic clays as the other main ore-forming minerals. You see examples of brecciated muds, perhaps related to slumping or perhaps related to dissolution. We can see gradations between more massive and diffuse laminar clays. We see obvious red oxyhydroxides and anhydrite layers, the grey zones there indicating the anhydrite-rich intervals. And then on the rightmost diagram, we can see laminated iron hydroxides interlayered with a variety of hydrothermal carbonates and manganese oxyhydroxides. So what's actually going on in this hot bottom brine? And notice, by the way, that when we enter the brine, this is from the Neom brine pool, which is a slightly shallower brine pool in the Red Sea, and that's the brine sampler going down through the uppermost brine interface. We can see that the brine layer, it's a zone where suspended sediment is accumulating. It's a combination of organics and inorganic suspended sediment. On the floor, within the brine pool itself, we see various combinations of iron deposition and manganese deposition alternating at the scale of individual laminae, telling us there have been some fluctuations in the lower brine. It's become obvious in the last decade that earlier studies underestimated the importance of the various non-sulphide minerals as metal-bearing components, where the metal absorption is forming onto what are polycrystalline silica iron hydroxide particles. Remember back to the brine chemistry, we had some of the highest levels of silica and iron in the bottom brines in the Atlantis II Deep brines compared to the brine pools across the rest of the Red Sea Deep. Now, during diagenesis, these crystals age, they mature, and so the crystallinity of all the various phases increases, and that aging also enhances fine layering in that sediment. And so within a few metres of burial, which is about a few thousand years, we start to see diagenesis coming to dominate. We see biogenic carbonate dissolving, we see manganose siderites precipitating, and the metals, which were originally in a relatively poor crystalline phase, dispersed and finely grained, or in the pore waters in those sediments, are being incorporated into diagenetic sulphides, and we see euhedral crystals growing orthogenically, both as sulphides and clays, and as well as iron hydroxides. There's also some high permeability in this sediment, especially in layers where we have significant levels of radiolarian tests, and they become a focus for later hydrothermal alteration and a focus for the deposition of amorphous silica and enrichment in elements such as barium and gold. So here's the typical laminated sediment nature in three of these images, where we can see the fine-grained sulfidic ore phases and also the orthogenic clays. Notice that the interlayered sulphide phases, which are interlayered with detrital sediments, the interlayered sulphides are quite dark, reflecting the anoxic nature of the environment. And then we can see the anhydrite in the non-metalliferous phases. These are hydrothermal anhydrites. These are forming by the cooling of 200 degree plus centigrade brines cooling on the brine pool, and we're precipitating nodular anhydrite in contact with, in this case, an underlying laminated sediment. In these systems, all of the sedimentology indicates accumulation and settling, and then subsequent diagenesis in conditions of bottom anoxia, quiescence, hypersalinity, and quite elevated bottom temperatures. It's the cooling of the brine that's driving the precipitation of these phases. The brine chemistry over this time frame of millennia are quite dynamic, and they're fueled by varying inputs of hot brine into the depression, and also some loss of the brine fluids via overspill and seepage. Overspill when the brine tops the brine pond margin, and seepage as these dense brines sink back into the underlying succession. And so in zones where we have hot dense fluids entering into the deeps, those fluids will rise and mix in that bottom brine layer until buoyancy and cooling causes them to reverse direction and sink to the bottom. This ongoing supply of hot hydrothermal brine from a combination of salt dissolution and focused escape of hydrothermal brines moving through the volcanics and the volcaniclastics gives us a brine reservoir, a dao, and it leads to the formation of oxygen-poor environments. And then within that environment we see convection caused by the double diffusion of salt and heat within those lower layers or in the brine sumps give us the stratification and the layering over time. Quenching of that hot discharging fluid, cooling of that fluid, leads to the precipitation of fine-grained ore material, along with other phases as well, silica and so on. And so we see copper-zinc ore accumulating syndepositionally to form massive as well as stratified sheet-like ore horizons. Once again, this is a contrast with the classic sedimentary strata-bound copper deposits, where we have epigenetic, diagenetic formation of the sulphides. Here it's syndepositional, not epigenetic, and it's created to quenching of a metalliferous hydrothermal brine. This process is little different from what happens on many mid-oceanic ridges, where we form metalliferous black smokers on the Pacific Ridge, the Atlantic ridges, where we form these ore deposits created by the cooling of metalliferous hydrothermal waters in rift zones on the seafloor. What's different here is that quenching is taking place within brine pools created by the presence of solder-Lochthon sheets supplying brines into those bottom pools. So what's different here is that we have, at the plate scale, we have continent-continent proximity in an opening rift. And so we have, before the mineralization takes place, a precursor formation of what is a halokinetic megahalite basin. And then within the central spreading zone, within this megahalite basin, we have hot metalliferous fluids rising into the brine pools created by the dissolution of that megahalite. So in terms of the sulphides that are forming here, and here we're showing you some sphalerite in a clayey matrix. It's quite euhedral. We also have dispersed chalcopyrite, but we also get other non-sulphide phases such as the silica iron oxyhydroxides and orthogenic clays. And here we can see some orthogenic clay minerals as well as some orthogenic iron hydroxides indicated by their pristine shapes growing during diagenesis. And so these are also absorbing metals. So these are relevant metalliferous sediment components in addition to the standard chalcopyrite and sphalerite zinc sulphide components. There's another interesting aspect of the sedimentology. If we look at the grain size as reflected in porosity in these what are hydrothermal sediments, the Atlantis II Deeps and also the Wandoo for that matter are ultra-fine sediments. On the right-hand side of the standard plot fields for deep oceanic sediments, which are plotted for sands, silts and clays for oceanic sediments worldwide, and we can see that in terms of depth to porosity, the Atlantis sediments are very fine-grained, very high surface areas, and accordingly very high levels of retention of fluid in the pores in that sediment. These hydrothermal sediments exhibit what we could call extreme characteristics if we compare them to the typical onshore and offshore sediments worldwide, as indicated by the three shaded fields for sand, silt and clay. Because of their ultrafine grain size, they have very high specific surface areas, and so their in situ water content remains above the liquid limit throughout the upper 20 metres where metalliferous sediments are accumulating in the Atlantis II Deeps. This uncharacteristically very high maximum void ratio and compressibility because of that result in very low sediment density profiles. And these are very different from the density profiles we measure in background Red Sea and other sediments, such as we see in the Valdivia non-metalliferous pool, which you can see is plotting quite clearly within that silt range of depth to porosity compaction ranges in the sediments. And we'll come back to this idea of ultrafines a little later when we look at how do we mine such systems. So these fines aggregating in the Red Sea brines form these low density flocks with Stokes terminal velocities, which are much, much lower than convective velocities in stratified layers. They settle much more slowly. And so they tend to experience quite long residency times in the convective brine pool, exposing it to conditions where there is more metal absorption. And we have these brine-soaked ultrafines with their inherent high surface areas giving us long-term exposure to mineralizing conditions in the brine column. Now, in terms of mining, that could be a potential future problem because we'll very easily stir up the mud and see high levels of nepheloid formation and fouling as part of the mining operation, which is going to be very difficult to control. If we look at the vent distance, the distance from an active hydrothermal vent to the levels of copper and zinc in the sediment, we can see that vent distance is not a significant factor in the distribution of mineralization in these sediments. The proximal sediments indicated in red have the same range of copper zinc weight percents as the distal sediments indicated in yellow. It's telling us quite clearly that it's not simple cooling that's causing mineralization in these brine pools. The distribution of the mineralization is also related to convective mixing of ultrafines across a stable anoxic basal brine layer. We see mixing and spreading of the mineralization so that it's centered in the vents, but the precipitative process is slow enough because of very slow settling rates that we see a distribution across the extent of the brine layer. It's also interesting if we look at, as we mentioned earlier, the carbon-13 values and also the ratio of the lightest hydrocarbon, methane, to slightly heavier hydrocarbons, the C2, C3 range. We're not looking purely at microbial signatures in the methane dissolved in these brine pools. That's the purple shaded area. We're looking at conditions with carbon-13 values much more indicative of thermogenic hydrocarbons. These are thermally maturation derived hydrocarbons, not the products of biochemical methanogenesis. We do see degradation of ethane and propane, but what's interesting here is that the ratio of methane to the higher hydrocarbons, the C1 to the C2 plus C3, is in the range of 5 to 570. It's underlying the very likely thermogenic origin for a significant proportion of the hydrocarbons dissolved in those brines. Several processes could be controlling the stable isotope ratios and the concentration of methane in those brines. It could be the result of thermochemical sulfate reduction, which requires temperatures in excess of 100 degrees centigrade. It could also be related to the secondary microbial degradation of hydrocarbons at temperatures of less than 60 degrees, or the secondary oxidation of methane at brine-seawater interfaces. These are all possibilities. But what's interesting here is that we very likely have a thermochemical input into these brines, not the standard microbial origin of methane. The much larger volume of these hydrothermal copper-zinc resources within the deep, compared to the much smaller volumes we see in near-vent precipitation sites of the typical VHMS, the volcanogenic hosted massive sulphide deposits such as Stag Mound on the East Pacific Rise, Smokers or Kuroko, or the Cypress-style deposits, they're much smaller. And the big difference is the effect of that brine pool. And that is related to the hydrological and hydrogeochemical effects of dissolving nearby halokinetic Miocene salt. And so that's what distinguishes this very voluminous, widespread cupriferous hydrothermal Red Sea precipitates from their much less stable cousins, the open seafloor hydrothermal brine pools, which are tied to much smaller extents related to hydrothermal outflows on the deep sea floor, where we get deep sea exhalative deposits. These are both a type of exhalative deposit. But what we have in the Red Sea deeps, we have brine soakers, not the much smaller scale black smokers we see in the typical deep sea exhalative deposits. In other words, you can say that the presence of widespread salt makes it bigger and better, because halite dissolution, which is replenished by ongoing salt flow into the sump, maintains an anoxic, hypersaline, stable bottom brine layer in the Red Sea deeps. And so with ongoing fluid escape about the salt sheet edges, so we see salt edge rocks forming here, in combination with convective upwelling of magmatically driven metalliferous hydrothermal fluids focused by the underside of the flowing salt sheets, and also the upwelling associated with the rift axis itself, creates bottom brine layer conditions that are highly saline and somewhat acidic, and they're suitable for widespread metal sulphide precipitation as those brines mix and cool. And so the precipitation and aging that's occurring occurs first at the halokine, but it also occurs in the brine column, and it's ongoing in the brine-saturated sediments beneath the brine pool extent, which is covering the bottom sediments with stable anoxic hydrogen sulphide enriched waters. So we see metal sulphides precipitating and then settling as laminates across large areas of the stable anoxic brine floor, not just near the vent output layers, but convective mixing with absorptive metal deposition across the brine pool. This combination of brine's pool stability, bottom quiescence, and an associated lack of mixing with any overlying seawater allows us to accumulate stable, widespread, laminated metal sulphides, and also to then allow those metal sulphides to mature in the sediment column. So the present-day thickness of our sedimentary strata in Atlantis II is about 20 metres, and they're overlain by something like 150 to 180 metres of stratified brine, made up of a lower and an upper brine layer, and various layered interfaces which become progressively more seawater-like with height above the brine. The metals in the brine lake floor have four main sources, which we'll call S1 through S4, and four different entry pathways, which we'll call P1 to P4. S1 is the ongoing normal background sedimentation that's bringing our biogenic pelagic and detrital silicic particles into the deep. They're settling down into the deep. S2 is our source areas for the hot hydrothermal brines, which is formed by deep seawater circulation through the underside of the evaporites and through the fractured basaltic system. S3 are sourcing somewhat cooler bottom-hugging brines and deeper pore fluids that have reacted mesogenetically with the surrounding sediments before entering and moving into the deep, brine reflux if you like. And S4, the other source, is the Red Sea deep seawater. And so the precipitation environments on those sources, P1 is the precipitation of sulphides in high temperature upflow zones, the typical VMS type deposits. P2 is the sulfidic plume fallout, and because there is an extensive area of brine stabilising that bottom layer, we see very extensive movement of P2. P3 is where we have absorption onto surface active silica iron hydroxide particles, and these have only become well documented in the last 2 decades, and then they settle down through that metalliferous lower brine layer and accumulate on the bottom. P4, the precipitation mechanisms are associated with ongoing aging and diagenesis within the sediment column. Coming back to the question I asked at the start of this discussion of the Red Sea copper zinc ores, are these SedEx or sedimentary copper deposits? Well, they're related to the cooling of incoming metalliferous hydrothermal chloride-rich brines dispersed over a long-term density stratified DAO, so they are not red bed copper deposits. Their metalliferous hydrogeochemistry and the formation of sulphides is driven by brine cooling. So it's a syndepositional hydrology, not the epigenetic hydrologies, the subsurface mixing redox hydrologies that characterise sedimentary copper deposits. The metalliferous pools, however, are created by a combination of salt flow at what is a growing salt ridge and salt dissolution. So salt dissolution is an important component here, like it was in the various stratobound sedimentary copper deposits. And also subsalt convective flushing is also important in this system as it was in the sedimentary copper deposit. The metal source is not leached continental redwoods, but it's tied to the hydrothermal leaching of these deep marine fractured volcanics. They're not sedimentary copper deposits in the terms of red bed source sedimentary copper deposits, but aspects of the hydrological focusing tied to the evaporites are common to both the sedimentary copper and the SedEx deposits, as we shall see in the other examples from this course, and also when we look at SedEx deposits and the importance of evaporites in creating giant SedEx accumulations in the lead-zinc world. One last thing to consider here is, can we mine these systems? Well, as yet, with the current equipment suites that are available for mining the seafloor, probably not. Most seafloor miners are designed to collect nodules on the deep seafloor. However, in these brine lake systems, we have very thixotropic lowermost sediments. We also have ultrafine sediment sizes, and so we have long settling time. So it's very easy to disturb the bottom sediments and create nepheloid layers or fouling layers which can become quite extensive with mining. Current techniques are not looking at controlling that disturbance of the bottom layers which is inherent to the ultrafine layers of these successions. And will have to be addressed in the design of future mining equipment for these rather interesting bottom brine copper zinc accumulations on the floor of the Red Sea.